Let's now take a look at compound options. There are basically 4 types of compound options. We have call on a call, and a call on a put, and a put on a call, and a put on a put. Now, in general, compound options do not have closed form solutions, but if we have special cases where the compound option, the option itself, and the underlying option are both European. So in this case, a call, for example, a call on a call, the first call is the option, but on a call, that call will be a underlying option. So a call on a put, the underlying option is, the underlying asset is a put. The option is a call on a put, okay? Now, if both the call, which is the option, and the underlying option are both European, and for the underlying option, obviously there's a underlying asset as well that is where this option is based upon, and that asset, that stock follows if that stock follows a log normal process, then the compound option um, ha has a closed form solution. So we have to have a few terms. So option C means the compound option. OU means the underlying option, whereas the option on an option. So this is the underlying option. And SU is the underlying asset for this option here, for the underlying option. Okay. It's a little bit complicated to talk about the relation because it's an option on an option rather than an option on a stock. Let's first take a look at a call on a call. So we denote that CC, call on a call. Let's say this option has a strike price K. Now this means that the option, the underlying option will be will have a price greater than K for that option to have a payoff, for the compound option to have a payoff, because the call on a call. And the payoff is that underlying call price minus the strike price, or 0. And has a maturity, the compound option itself has a maturity T. So let's say you're currently here, you have an option which matures at the big time T here. This option is, however, based on another call, which is the other call that matures at T star and started at this point here. That call is the underlying asset of the compound call, the call on a call. So we denote that underlying call as C star. And obviously that C star has a strike as well, K star. Now this K star is really for the stock price. So if the C star will have a positive payoff if the realized stock price at T star is greater than K star, okay? Now, so if you look at it, the compound call on a call, has a payoff structure that is a maximum of C star minus K or 0. So how are we gonna price it? Well, assuming here, both the compound option and underlying option are European, and the stock price follows a log normal process. We see that the price of C star is actually relatively easy to be determined if we know what the realized price of ST. So if we know ST here, we can find the corresponding C star price, which is actually given by the Black-Scholes-Merton formula here. Now, obviously, this C star depends on this ST. Okay, so C star is a random variable. Well, so what is then the price of the compound option? Well, the compound option is the discounted expected value of the payoff, and what is the payoff? Now the payoff here is really, when is this C star to be in the money to infinity? And look at that distribution there. So basically here we have S star is really the value of the realized ST such that C star is equal to K. So we're doing this and upward, meaning that we're integrating over the probability distribution that C star is a positive value rather than 0. Sorry, C star minus K is a positive value rather than 0. Okay, and so we're getting, so here is basically the expected payoff, and we're doing a discount here, and the payoff function is really C star minus K. And here, this fx is really the probability density function of a normal distribution. And so this relates to this S star value here, because we have selected a particular S star value, which is equal to, which makes C star equal to K. Okay, and since the call, so all the other value all the other S star value are the S star values. Sorry, all the other values taken by X are the ones where the log as some ST divided by S naught, where the ST is greater than S star. So once we have that, so this is basically a discounted expected value in risk neutral. And so the mean of the distribution, the normal distribution is R minus Q minus sigma squared divided by 2 times T. And the variance is sigma squared T. Okay, so we need to figure out what's inside of this integral. Now, if we substitute in the expression here, this closed form solution for C star, we'll have, this closed form solution minus K in the integration here, in the integral here. And then we can break this integration into 3 different pieces. One piece is related to this, one piece related to that, and one piece related to this K here. So that's exactly what we have. So we have 3 integrals here, okay? And once we're integrated, we put them together. So in order to calculate the integral here, notice that we're integrating in the integral, we have the cumulative normal distribution, and we have this probability density function as well. So we're having the product of the cumulative normal, standard normal, and the PDF, probability density function of a standard normal, inside our integral here that we need to worry about. And so what are they? So what is that, right? We know that if we have an integral, which is really the product of those 2 functions, the cumulative normal distribution and the probability density function of normal distribution, we can actually derive the. Now to calculate the actual value of this integral, let's first substitute this st, and we know st is equal to s naught times e to the power r minus q times t. So let's substitute it in. We have this expression here. Okay. Now, if you, because these two together, you can add them together on the exponent. So it becomes really just s naught times e to the power minus q t star. Okay. Now, then we need to know this part. Okay. So we know that this is from statistics. If we have an integral from some number a to infinity of the product of cumulative normal distribution with a that is on a random variable bx plus c, and times the probability density function of some random variable x, we then know this is this integral itself is a bivariate standard normal cumulative density function. So basically, this m function gives us the cumulative probability where random variable x1 is less than alpha, random variable of x2 is less than beta, and the correlation coefficient between x1 and x2 is rho here. And rho is then given by this particular condition. So just take this as given, and let's see how this will help us to derive our formula here. So for a call on a call, we have that so in order to use this condition, we have to figure out what A, B, and C are. A, we know, is basically the starting point of the integration. So the starting point of integration is this. So we know that A is basically log S star divided by S naught. And what is X? X is really, the variable, which is log st divided by S naught. And S naught is really a constant, so it's really, this is the random variable there. But X is basically the log of this ratio. So we have to figure out B and C. Note that we have to do this integration for ND1 and ND2. So we needed ND1 here. And for the second part, we need ND2. So for each of that case, we need to figure out the corresponding B and C. If D1 is equal to Bx plus C, and we also need to figure out B and C if D2 is equal to Bx plus C. Okay, so given this A here, and for D1, you plug in D1 here, we'll find that B is equal to this and C is equal to that. Okay, and you will put in D2 is equal to bx plus c, then b needs to be this, which is the same as in the situation of D1. But for C, the sign is different here. So plus sigma squared divided by 2 here is minus sigma squared divided by 2. Now for each of those integrals that we need, we figure out what A is, what B is, what C is. We know mu, we know V. Mu is the mean of fx, and V squared is the variance of this probability density function. And we know rho through this condition here, then we can basically integrate them. Now suppose you drill through all the math behind it. So essentially integrate those three, and we know how to integrate 1 and 2 now with this condition. And once we figure out B and C, and then this integral is actually very easy. So let's say if you have gone through everything, now we will basically, the call on the call will just have this expression here. This m is, this 2 m's here are the bivariate standard normal distribution. And with this this being alpha is the beta, and this is rho. Okay, so then once you apply to that, alpha, which is in here, it's A1 is equal to this thing. A2 is equal to that. B1, which is alpha, which is beta in this thing here. You will get this expression for B1, and B2 will be this expression here. And this is rho, the square root of t divided by t star. And this is a simple one. You see there's an n A2 here from this integral. Okay, now you basically have got a closed form solution for the call on a call. You just need to have a bivariate normal distribution here in order to get the price. So I'm not gonna go through the math. You can figure them out. We have enough material to figure them out. And so if you apply the same stuff, a put on a call formula will be this, and a call on a put will be this, and a put on a put will be this. Okay, we know what the A1, A2, B1, B2 are, so we can price them. So essentially, the important part of calculating compound options in order to derive the closed form solution is really to recognize this equation here, where a compound option is just a discounted value of an integral here, where here, the first one, you substitute in the payoff function of the underlying option. And once you recognize this and you know the condition, you know what this thing is, which is this, then you're able to derive the formula for all 4 different situations.